Simulation Summit for 2022. And one of the big deals about this one is that we're introducing VCIM12. So I want to welcome you all, and I'm just going to say a few words here, and then I'll be handing it over to Dr. Andy Yu. So I think many of you who are here know what TechX is all about. What we focus on is plasma simulation, primarily with VCIM. We do have an RSIM product as well, but this is what we're mostly going to be talking about today. TechX Corporation provides simulation software that contains all of the needed physics for doing and modeling plasmas. It has charged particles interacting with external and generated electromagnetic fields, extensive collision processes, extensive boundary processes. It has complex geometry, and that truly sets it apart from other plasma simulation software packages. It's high performance. It can be run on anything from a laptop to a supercomputer. It's just the bigger problems you have, the more compute power you want. And it has ease of use with a nice graphical user interface. So to summarize, what we do at TechX is we bring the latest advances in physics and computational research to solve complex real-world problems, especially in the area of plasma physics. So TWSS, again, TechX Worldwide Simulation Summit, will describe and demonstrate the latest capabilities. You're going to see over the next few days, next 2 days, that we've greatly enhanced our reactions with an unlimited number of reactants products, and those can be limited to surfaces. You're going to see that visual setup has been significantly expanded so that you can now do external circuits, which is very important for doing things like magnetron sputtering or various kinds of arc breakdown. We now have the ability within the graphical user interface to do parameter scans, and we have a new word for analyzing those scans, and that's what we call scanalyzers. Please forgive us the portmanteau, but we're trying to move in the tradition. So another thing, you may recall me talking about speed-limited particle and cell, I believe it was last year, and this is a way of keeping kinetic electron effects, even though you're studying slow ion scale phenomena, and doing so while eliminating the high-frequency plasma effects from the problem so that one can solve them accurately, get the physics correct, without the requirement of the very tiny time steps that typical electron simulations require. Well, last year it was under development, it was research, and now this year you're going to see that it is now available within VCIM. And of course, we keep adding and putting more things in it. Now, this is especially good for the Townsend problem. The Townsend problem is originally a problem of breakdown between two plates where you put a voltage on it and you ask how much does the signal, the current get amplified by the fact that as the electrons are traveling through the gas, they cause ionization, which creates more electrons. So as we said, presented last year in VCIM this year. Now, one of the cool things about that, I think, is that this allows people to compute breakdown. What happens in the Townsend problem is, of course, that when you get exponential growth, well, that tells you that the whole system is about to arc. And for many situations, what you'd like to do is figure out whether that breakdown is going to occur, because of course, if it does occur, then you'll have major problems with whatever device you're trying to design. So what one can do is combine those two things, the scans with their scanalyzers and the speed-limited particle and cell, and do a number of simulations of any particular configuration at a number of different voltages, and look at each one of them and figure out, hey, did this simulation have exponential growth in the number of particles? Well, if so, breakdown occurred. Oh, it did not? Then breakdown didn't occur, and it's okay to operate at that voltage. So the ability to compute breakdown is really significant, we think. And then finally, there is not finally, but penultimately, there's video creation. This is a new feature in the GUI where you can stitch together your images and create a movie of it. And that's especially important. And I know that for many of you, what you're doing here is you are trying to do the physics that you need to do to help your company or your unit or do for your project. You want to try and do the physics that you need to do in order to get an answer about how to configure a product or doing research in the university setting. Well, in order to do that with VSIM, of course, you have to go convince your manager that VSIM is a good product and it will help you do the physics you want to do. And there's nothing better than a good movie to help you make that convincing point. You're also going to see that we have tons of examples, new examples for breakdown, for magnetron sputtering, and more. And there will be a series of talks over these 2 days that tell you all about that. So I want to invite you then to just sit back and relax, enjoy the show. And I'd like to introduce our next speaker, Dr. Andy Yu, who comes to us from Boise State, where he got his PhD. And he has been a VSIM user for a long time, even as a grad student. And now, of course, we're lucky to have him at TechX, or employed by TechX, because he's still located in Boise, but employed by TechX, where he's going to show you a number of the new features of VSIM that are in VSIM 12. So thank you.
Sure. All right, I assume everyone can see this fine. So welcome again. My name is Andy, as John said, and I'm an applications engineer at TechX. In my presentation today, I want to show you how you can use VSIM to explore the fundamental physics of complex devices. I will use my own research in cavity magnetrons as the example here, but the general workflow applies to other research as well. I want to lead today's presentation with a quote from renowned French music conductor Nathalie Stoltzmann. There are 2 types of artists, those that strive their whole life to show how much what they are doing is difficult, and they do have their audiences. Then there are those who spend their life trying to make people believe that it is not at all difficult, which is the category I belong to. That is also probably a form of madness. It is less spectacular, perhaps, but I prefer that the audience be able to go to what is essential in the music. I do not want them to stop at being impressed with the performance, even though they might notice it, but that they may be able to abandon themselves in the beauty of the music. Although she was talking about musical performance, in this quote, replace every word music with the word science. I believe her principle applies to scientific works as well. With that, let's start with the essentials. The scientific method, everyone knows this. This is what brought humanity out of the Dark Ages, and this process is fundamental to all modern scientific progresses and understanding, and to a certain degree, I believe social progress as well. Although the method is often presented in this type of neat circular flow diagrams, as we all know, in practice, things can get a lot more stochastic, as we like to call it, a lot more random. For example, if your research is in a frontier area, there might not be much background information available for you to do your background research. In many situations, you might not even have a clearly defined hypothesis. or the results of your experiments might not be conclusive, etc. But in any case, testing and experiments are essential. This is not to say science is all about testing and experiments. Theoretical works provides the hypothesis to run experiments for, as well as providing tools for efficient data analysis. Now, contemporary computer-aided engineering, or CAE as people call it, these tools have matured to a point that the results they produce are widely regarded as data. Of course, everything ultimately needs to be verified by physical experiments, but physical experiments are not always feasible due to various constraints, especially in an early stage of a research. Vcim as a CAE tool is essentially a testing and experimentation tool, which is useful for both experimentalists and theorists. Unlike traditional quote-unquote brick-and-mortar experiments, which in this day and age involves significant, sometimes prohibitive capital and human resource investments upfront, Vcim allows contemporary scientists and engineers to perform the same experiments at a fraction of the cost, hence largely bypass the capital and human resource investment issue and makes contemporary science accessible to more people. And Vcim has many advantages over other CAE tools, as you will see throughout this presentation. RF technologies have really become the backbone of many aspects of modern society. They have prominent uses in communication, as they are widely used for applications related to object detection, heating, and material processing. RF can be generated via the use of solid-state devices or via the use of microwave vacuum electron devices, or MVEDs for short. The use for MVEDs predates solid devices, but in the past few decades up to today, solid-state devices are very popular due to their versatility. However, with the ever-increasing needs for higher power and higher frequencies, people have begun to shift their focus back to MVEDs, such as magnetrons, klystrons, and traveling wave tubes, and others. The figure on the right shows time on the x-axis, and the y-axis is a figure of merit, which is a combination of power and frequency. It is average power to frequency squared in megawatts, gigahertz square second, a very big unit. As we can all see, in terms of combined power and frequency, solid-state devices have been mostly stagnating since the 70s. This is, of course, due to its physical constraints that electrons have to collide with the material lattice for the interaction to happen. And you have power and frequency limitations on that. In contrast, MVEDs have continued to push into higher and higher power and frequency combinations, almost displaying a Moore's law-like trend that is still continuing. Despite their extraordinary capabilities, MVEDs present significant challenges, since making them to work as desired is not always easy to do so. And the physics behind these devices are not always well understood. My research focused on a type of MVEDs known as the magnetron. I am interested in the fundamental physics behind its operation, especially its startup mechanisms and how to potentially control it. I want to mention here that the word magnetron is used in many different contexts to mean very different things. You have cavity magnetron, which is what I'm going to talk about today. And you also have sputtering magnetrons, which we have a presentation for tomorrow morning as well. And you also have magnetron injection guns that is used in devices such as gyrotrons, and these are different devices, although they're all called magnetrons. So some background about the magnetron. The magnetron is one of the most common type of MVEDs that has many applications. Magnetrons have exceptional power efficiency, up to 90%, and very high power density. The magnetron anode is a slow wave circuit which can take many shapes, as you can see in this figure on the top. A single magnetron cavity can be viewed as a LC circuit, as shown in the figure below. The geometry of the cavities determines the inductance and the capacitance, which in turn determines the frequency of the LC circuit. The magnetron can operate in many different modes depending on the phase difference between one resonant cavity and its adjacent cavities. Maximum efficiency is achieved when the phase difference between adjacent cavities is 180 degrees or pi. The resulting operating mode is known as a pi mode. Magnetron operation is a chaotic process. During the magnetron's operation, the cathode emits electrons, and the electrons form a hub around the cathode. The magnetron is a cross-field device, namely the applied DC electric field between the cathode and the anode is perpendicular to the applied magnetic field. This field configuration dictates electrons in the system following a E cross B drift motion described by the Lorentz equation. The electron motion induces current on the slow wave circuit, and the feedback fields from the slow wave circuit causes azimuthal velocity of the electron population to bunch, and electron spokes begin to form as a result of this bunching. This process can be seen in the figure on the right. In subplot D, we can see the magnetron oscillating with 5 spokes. This is a pi mode for this magnetron since it has 10 cavities. This figure comes from one of my simulation results, and we will come back to it later. The RF fields are supported by particles giving up their potential energies to the RF field. In order for this to happen, the applied E and B fields must fall into certain ranges and maintain certain relations. Lots of detailed physics here, but I will not go into the details since we have a general audience here. One thing that's important to mention is that magnetron is a free-running oscillator by default, which means the RF phase of its output are not controlled. This significantly limits its use for applications that requires phase control. Finding ways to control magnetron output phase is an active area of research, which is an area this research partially falls under. So what capabilities do I need to simulate such a device? First and most importantly, I need self-consistent simulations of beam wave interactions. A computational combination that can reliably do this is finite difference time domain and particle in cell. Second, since my device is a cylindrical device that involves curved surfaces, I need my simulation to use cut cells for accuracy. Third, it would be great to be able to do CAD imports to make it easier to work with complex geometries. And last, and also very important, I need to be able to finally control the spatial and temporal profiles of the applied field and particle emissions so that I can run experiments to explore the physics. As you can expect, Vcim has all of these capabilities, so Vcim works as a great tool for MVED research. 2 magnetrons were modeled for this study. One is a 2D rising sun magnetron, and the other is the CWM 75 kilowatts, which is a commercially available product from L3Harris. Each magnetron model was simulated under 3 different priming conditions, that is no priming, RF priming, and cathode modulation. The term priming here refers to creating a simulation environment that's favorable for magnetron startup. Priming can be done via adding an external RF signal, modulating the electron injection, or varying the external magnetic field. Some of these techniques, such as cathode modulation, can be experimentally realized. Some of these techniques are mostly theoretical and help us to study device physics. I will not have time to go over all of these cases in detail. I will only go over a couple cases individually, then I will look at the results from all cases in aggregate, which is where the most interesting observations can be made. Keep in mind, the 2D model and the 3D model are of different devices. The rising sun magnetron model have a 2D geometry with no scaling. The dimensions are shown in the figure and the table here. In this case, since it's a 2D model, RF output was simulated by a power absorber in one of the cavities, as you can see in the figure, type loaded cavity. The cathode emission boundary can be, in this case, is circular, as is modeled as a cylinder, but in actual magnetrons, this cathode can take many shapes, sometimes a spiral, usually a spiral, and sometimes you'll have other exotic shapes as well. The simulation domain is 204 by 204 millimeter. The simulated cells are 2 by 2, so this is a relatively coarse simulation grid. But as you can see, it can still produce very good accuracy. The time step size delta t in this case is set to exactly 1/1000th of the pi mode RF period, and this is below the CFL limit. This time step is chosen very deliberately for our analysis later. And in this case, a 500 nanoseconds simulation takes about 1 to 2 hours with 32 CPU cores. And these are not even the latest CPU cores. So this simulation runs rather efficiently. Very quickly showing the 3D model specs as well. Note that this is a much larger simulation, and a 300 nanosecond simulation in this case takes about 2 days to complete with 32 CPU cores. And one thing I want to mention is in this simulation, a 10-sided cathode was used to simulate, for this simulation, to match a experimental configuration. And that is a cathode that was intended to be used with gated field emitter arrays to actually do this controlled injection that we are about to simulate. So it's not just a simulation concept, it's actually being experimentally realized. So first we simulate the device, the 2D device without any priming. This is our reference case. The model can start up very quickly without any priming in this case. This figure here in the middle shows the microparticle distribution at various time spots. In the beginning of the simulation, we can see the electrons being injected around the cathode. And a bit later in subplot B, at 100 nanoseconds, we can see the electron population is now showing a 3-spoke pattern, which corresponds to the 3/5 pi mode. Then at about 150 nanoseconds, the electron population begin to shift to the pi mode, which give you this 5-spoke pattern. And at 250 nanoseconds in subplot D, this magnetron is fully oscillating. And the figure on the right shows histories of cavity voltage, the emitted current along with absorbed current by the cathode and the anode, the physical particle count, and the output power. The current plot shows a noisy pattern before 200 nanoseconds and 350 nanoseconds, which suggests instability, possibly caused by mode competition. Then after 350 nanoseconds, the device seems to be operating in steady state. with the stabilization of property of cavity voltage, current, particle count, and output power. So the particle position plots and history plots are the most common ways to look at simulation results. While offering us with many useful information, they do have their limitations. The particle position plots show us where the particles are located at a certain instant of time, and we can observe this plot and see whether the patterns matches or our expectations and identify potential issues. However, one plot only shows one instance of time, and many plots are needed to see progression, as you'll see on the previous slide. 2D cross-sectional plots may omit important information if the simulation is in 3D. And 3D particle plots can be hard to read. And more critically, these plots offers minimal information about the particle's movements. The history plots show us macro level quantities of interest. These are usually numbers representing certain aspects of the total system. While revealing many useful information, these macro level quantities often fail to capture micro level activities, which are often critical for understanding settled device physics. So it is natural to wonder, what if we can have an analysis method that shows the behaviors of the particle population and how they change over time, so that we don't have to try to analyze large collections of particle positions or velocity plots? And what if we can have an analysis method that generates statistics of the particle population's movement and how they change over time? So my first solution is the electron distribution intensity plots, as shown here. Each plot shows the normalized probability masses of an attributes of interest and how they change over time. The generation of these plots involves a lengthy process. I will not go over the details for the sake of time, but I want to point out that this type of processing is possible because Vcim allows the user to access the complete suite of data of every particle in the simulation. That includes positions and velocities in all directions, the microparticle weights, and even the particle tags that allows distinct particles to be tracked across data dumps on a massive scale. So the first attribute of interest is the radial position, as shown in subplot A. This plot shows the position distribution of electron population in the radial direction. Darker color denotes higher probability in this case. For example, in the beginning of the simulation in region 1, we can see that areas near the cathode are very dark, and areas near the anode are white. This means that it is very likely to find an electron near the cathode and nearly impossible to find an electron near the anode in the beginning of this simulation, which is what we expect. Also in region 1, we see the dark areas expanding towards the anode, which indicates electron population is expanding in the radial direction. And the electron population reached the anode in region 2. The same analysis was done to radial velocity as seen in subplot B. We can see that in the beginning of the simulation, the radial velocity distribution has a balanced spread near 0. When charge transfer began to happen in region 2, which is when the magnetron began to oscillate, the distribution shifts into the positive regime, which is consistent with our expectation for charge transfer. The azimuthal position plot is unique since the azimuth of the cylindrical geometry forms a complete circle. So the bottom of this plot is actually connected to the top of the plot. Since the time step delta t is exactly 1/1000th of the RF period, and electron data was dumped every 1000 steps, electron data was dumped as the exact end of every RF period in this case. Therefore, if the device is indeed oscillating in the pi mode, the azimuthal position plot should have 5 perfectly horizontal lines. Deviation from these lines indicates frequency instability. In this plot, we can clearly see that the pi mode pattern emerging out of chaos. The fuzzy lines in region 3 indicates frequency instability, which confirm with our previous observation that we have mode competition in the system during that regime. And azimuthal and the lines in region 4 is quite clean, indicating the frequency is stable. The azimuthal position plots given the appropriate data dump period functions as a great diagnostic for frequency and phase stability. The azimuthal velocity plot also shown, that is subplot D, also shown the previously observed instability in region 3 with its spiky patterns. Works are currently being done to compare this azimuthal velocity distribution to the phase of the RF circuit. In this plot, red lines denotes average. The oscillating pattern in region 3 again indicates instability, and the flat averages in region 4 indicates stability. If you are familiar with analysis of particle data, the electron distribution intensity plots are essentially phase space plots with the added dimensions of time. These plots free the researcher from sliding a time bar up and down and sense information and shows information throughout the simulation. And since all the information is displayed on the same plot, it makes key pattern a lot easier to recognize, as you can see, especially in subplot C. The other new analysis technique is the breadth ratio analysis. For this analysis, we first define a nominal direction of movement for each axis. In the context of our cylindrical magnetron, the nominal direction of movement in radius is a positive radial direction, since we want electrons to flow from the cathode to the anode. The nominal direction of movement in azimuths is a positive azimuthal direction, since the direction of our external magnetic field dictates the electron spoke will rotate in the positive azimuthal direction when the device is oscillating. Now, at a given time spot, if particles have a positive velocity in the nominal direction of movement, we call this particle an advancer. If the velocity direction is counter to the nominal direction of movement, we call this particle a decliner. And the breadth ratio for each axis is simply the ratios between advancers and decliners. In short, the breadth ratio in radius reveals the level of internal support for charge transfer from the cathode to the anode. We will explain this when we look at specific plots. And the breadth ratio in azimuths reveals the cycloidalness of the electron population. It's not only reveals, it actually quantifies it, because the ratio is a number. It's a simple number. As shown in this illustration here on the bottom, on the top right, subplot A shows a highly cycloidal electron trajectory. In this case, a significant portion of the electron trajectory is in the declining state, as indicated by the blue arrows. And in this case, the breadth ratio in azimuths would be very low, because it's essentially the comparison between the length of the green vectors versus the length of the blue vectors. If the electron trajectory was less cycloidal, as in subplot B, a lesser portion of the trajectory would be in the declining state, which will lead to a higher breadth ratio in azimuths. If the electron trajectory is near Brion flow, that is, it is not cycloidal at all, as shown in subplot C, then the breadth ratio in azimuths would ideally be infinite in this case, since we have no declining states. Now let's look at the breadth ratios for our simulated electron population in the rising sun magnetron in the bottom plot. In region 1, we can see the radial breadth ratio stays around the 1-to-1 level. This means for every electron moving towards the anode, there's an electron moving away from the anode. As a result, the electron population has no net movement towards the cathode. The ratio begins to take off in region 2 and wildly oscillating in region 3, again indicating instability in region 3. And then in region 4, the ratio holds at about 3.8 to 1, which means for every 3.8 electrons moving towards the anode, there's only 1 electron moving away from the anode, indicating a net movement towards the anode, with the radial breadth ratio holding at 3.8 to 1, the electron population offers continuous support for charge transfer from the cathode to the anode. And for the azimuthal breadth ratio in subplot B, we can see the ratio stayed quite low prior to oscillation start. And more interestingly, even after steady state was reached, this indicates that the electron population was highly cycloidal before and even after the device oscillation reaches steady state. We will discuss the 2D and 3D results together in later slides. The point of this slide is to show you the type of control that Vcm gives you. In this case, I want to inject electrons at 5 evenly spaced locations that rotate around the cathode to match the phase of the RF field. This uncommon simulation setup was to accompany the experimental setup that we were doing. In Vcm, you have complete control over where and when particles are emitted and introduced into your simulation. In this case, my electron injection was described by this very messy function you see under the third bullet point. And the result of this function, as you can see in the particle distribution plots in the middle top plot, is that we have exactly what we want in this case. We have injected electrons at 5 distinct locations, and these locations rotate to form this oscillation. Lots of work was done analyzing the simulation results. Here I will only show you the most exciting parts. Some interesting patterns become obvious when we put the breadth ratio plots of all cases together. That's all 6 cases across the 2 different models. The plot in the middle shows the rising sun magnetron cases, and the plot on the right shows the 3D CWM 75 kilowatts simulation cases. And out of all 6 cases, we have 4 cases that reached stable oscillation. The cathode modulation case for the 2D has some issues, probably because the way I was doing the cathode modulation kind of fights with the rising sun geometry, because it's a sort of a specialty geometry that have multiple modes in there. So that case didn't work all that well. So we can omit that case. And the other case that didn't reach oscillation was a no priming case for the 3D model. So chances are I still need to optimize this model, because there is a research paper by University of New Mexico that was managed to make this model oscillate without priming. So we omit those 2 cases and we look at the 4 cases that oscillate. So we can see a stable startup always results in a breakaway and hold pattern in the radial breadth ratio plots, as you can see in the no priming and RF priming cases for the 2D and the RF priming in the 2D. So right, and more importantly, in all cases that oscillated, the azimuthal breadth ratio always dipped lower right before oscillation starts, as you can see in the 4 cases that oscillates. So one note on the breadth ratio, on the radial breadth ratio for the 3D case, you can see it's try to break away, then it fails. This is caused by the way that when those spokes touch the anode circuit in the beginning, it formed something we call a super spoke, that the anode begin to suck particle out of the system very rapidly. So that causes the azimuthal, the radial breadth ratio to collapse, as you can see here. And I have discussed with some industry people, and I have been informed that in magnetrons like this, sometimes you go through several of those startup and breakdown cycles before a steady state is reached. And in this case, my simulation ended at 300 nanoseconds, so I don't have a chance to see that. But the observation in azimuthal breadth ratio is what we want to focus on here. So more interesting observations can be made when we look at the analysis plots from a different perspective. These plots shown here are from the 3D simulation of the CWM 75 kilowatts. But the same observation were also made when studying the 2D results. Here are the observations. We know that oscillation startup requires a radial expansion of the electron population to open up the possibility of charge transfer from the cathode to the anode. This radial expansion can be clearly seen in the radial position distributions on the very top. However, if we look at the radial breadth ratio, that's the 2 subplots on the bottom, during when the radial position was expanding, we see that the ratios remain flat, which indicates that the radial expansion of the electron population is not supported by the electron population's net radial motion, which is counterintuitive. At the same time, we see the timing of the azimuthal breadth dip coincides with the timing of the radial expansion of the electron population, suggesting strong associations between the 2. The reason why I use the word association here is that note near the end of this simulation, the azimuthal breadth ratio is also very low, but the electron population did not expand or show the same expansion pattern, which means the azimuthal breadth ratio dip is likely a necessary condition for radial expansion of the electron population, but it is not a sufficient condition. There are other factors also at play here. So what does this tell us? The hypothesis I have is that the increased cycloidal motion of the electron population creates a very dense electron population near the cathode as the electrons turn around in their cycloidal orbits. Because the velocity is very low when they make their cycloidal loop, the electrons spend more time near the cathode, as seen in the radial position plots. As a result, electrons are propelled from the cathode due to the Coulomb force and cause the electron population to expand towards the anode. So that's the new hypothesis. So let's summarize what the process so far. So we started with a hypothesis that is not well defined because theories on magnetron startups are incomplete. We proceed by simulating two different magnetrons under various setups. Some of these setups are inspired by physical experiments and obtained trustworthy results from Vcm. We analyze the results with standard techniques as well as finding new techniques to look at old results in new ways. And we made observations that lead to updates and modifications to our original hypothesis or the forming of new hypotheses. Then the natural next step here is to repeat this cycle and test our new hypothesis. So in previous results, we see that the Breast ratio consistently dip, the azimuthal breast ratio to be specific, consistently dip prior to oscillation start and concluded that there may be association between the azimuthal breast dip and magnetron startup. So it would be natural to see what would happen if we inject electrons in ways that induces low azimuthal breast ratios. The way I did this was by what I call electron counter injection, which I define as the act of emitting electrons from the magnetron cathode with an initial azimuthal velocity with a direction that is counter to the direction of expected rotation determined by the direction of the applied magnetic field. So electron counter injection is expected to increase the level of cycloidalness of the electron population because with previous terminology, you are essentially adding decliners into the system. For the sake of simplicity in this study, I fixed the initial azimuthal velocity with an amplitude of about 5.3 10⁷ meters per second in the counterclockwise direction. This velocity was determined by iterative parameter sweeps, and this velocity seems to induce the pi mode oscillation the best. Now the level of cycloidalness can be altered by changing the percentage of electrons that are counter-injected. The ratio of counter-injection was swept from 0 to 1 in 0.1 increments. So this type of analysis is where the parameter sweep come in very handy when you need to run a massive amount of the simulations. So in this case, for each, I run 11 cases for total. The difference between the three group of plots you see here are time, which is labeled on the bottom of each group. So in this case, a ratio of 0, when the ratio is 0, all electrons were injected uniformly, which is our reference case. On the other hand, when the ratio is 1, all electrons were counter-injected. By the same logic, a ratio of 0.6 indicates 60% of the electrons were counter-injected, while the other 40% are injected uniformly. The left plot is at 25 nanoseconds, which is very early on in the simulation, and the middle group is at 75 nanoseconds, and the right group is at 150, which is right before the onset, which is as the onset of oscillation. Lots of information here, and I don't have time to go through everything, but I want to mention 3 most important implications of this study. So the first implication is that electron counter injections have effects on the startup process, as you can clearly see, though the physical mechanism by which these effects takes place are not yet clear at this point. And second, electron counter injection, when applied correctly, clearly speed up spoke formation and shortens oscillation startup time, as you can clearly see, especially in this middle plot. When the counter injection ratio is 0, you are still struggling with the 3/5 pi mode, and with a higher ratio, you can begin to see the 5-spoke pattern already. So the third implication is that after the magnetron is oscillating, which you can sort of see in the right plot group, counter injection seems to be of no further help to the characteristic of the oscillation. Rather, it's actually adds noise in this case. So ongoing work includes continuing this electron counter injection study, developing new analysis techniques, and extending this type of research to other MVEDs. I will not go into the details for this since most ideas and results have not been published. But I do want to mention is that work is being done to integrate the electron distribution intensity plots and breadth ratio plots into the Vcm ecosystem, so that all Vcm users will have easy access to these analysis techniques presented earlier in this presentation. This presentation have demonstrated that Vcm with its robust algorithms produces trustworthy results. Vcm grants its users complete control over the simulation and will not stand in your way when trying out novel setups. Besides its built-in data visualization and analysis capabilities, Vcm also allows easier integration with most programming languages for sophisticated data processing. With all these pieces in place, Vcm serves as an essential link in the scientific process. But this work was conducted under the direction of Dr. Jim Browning, who was my PhD advisor, and I would also like to thank AFOSR for funding this research throughout my grad school. And here is a list of publications and presentations that was based on this research. And with that, I will take any questions you may have, but please keep your questions general for general audiences here. If you are interested in a discussion regarding specific technical details, please email me directly at the email listed here. And yes, I do read all my emails. So if you want a discussion, just email me. And let's see if there are questions.
Yeah, that was fantastic, Andy. Thank you so much for doing that. As Dr. Carey said at the very beginning, we are certainly pleased that we have Andy here as an application engineer for us. There is a Q&A box where you can type in questions on the bottom and I can read them. Andy also put his email there, as you see, which in many cases is a little bit easier than with asking the questions here, especially if they have a lot of technical details, and we definitely want to assist you. Our next talk is coming up in just a few minutes, and that's going to be Dr. Ming-Che Lin. So I think maybe one or two, if you want to type them in the Q&A box, and we can take them. Otherwise, we'll move on to the next. We have, for the rest of the day today, we have 2 more presentations, and then tomorrow we will have 3. We also have, Andy is so kind that he's going to deliver this for us again tonight to reach our clients over in China and Japan and all that, since it's a little challenging for them.
I see we have a raised hand by Robert.
Yeah. Let's see. I'll try to. Can you type your question in the chat box, Dr. Bob Terry, if possible? That was really good, Andy. I'm so excited to actually be able to see a little bit more of your background, you know, and the stuff that you've done before coming here. I still remember when Andy applied to work with us, and I was like, oh my gosh, he's been using Vsim this whole time. We were super excited that we were able to convince him to come be with us. So if anyone has one last call.
I don't see the question yet. So maybe just email me directly, and we'll have 4 minutes till the next presentation.
Yeah,
so
that's fine. We'll go ahead and we'll go ahead and get Ming-Che set up. So thank you again, Andy. Thank you very much. And I will go ahead and we'll get Ming-Che and his presentation coming up in just a few minutes. Thanks so much. All right. Hello again and welcome. We will probably wait till about 10:01 for our next presentation, just to give everybody time to come in through the application and get set up. And I feel like saying we're back for the next presentation. Welcome to TWSS2022. Thank you so much for joining us. Hello, Ming-Che, how are you?
Good, can you hear me?
Yes, I can hear you just fine. I know it is, gosh, what, middle of the night for you right now?
Yes, yeah, it's a 1 a.m. in South Korea.
Oh my gosh, oh my gosh. Well, thank you so much for doing this. We're always excited.
If your audience cannot understand my talk, that's okay. You can watch the video again.
Well, and I want to let everyone know that we are going to have the videos for all of the presentations on our YouTube page. Once this is all finished, we'll clean them up and we will get them there. And similar to last year, we will make PDFs and PowerPoints available for download off the website as well. So we have a lot of the ones from previous years on there right now. If you have any questions today, I want to let you know we like to hold questions till the end, and there is a Q&A box on the bottom of your screen where you can type them in, and we will do our best to answer those. And let me go ahead and welcome Ming Che. So Ming Che has actually received his PhD in electrophysics from I won't even say that, Ming Che, from a university in Taiwan in 2002. He's currently a professor with the Department of Electrical and Biomedical Engineering at Hanyang University in South Korea, where he's involved in particle cell simulations of plasmas, microwave tubes, electron emissions, and terahertz wave sources. And first principles computations of surface physics and heavy ion therapy. He is also the founder of the multidisciplinary computational laboratory, Hanyang University, where he is focusing on combining computational electromagnetics and quantum mechanics for studying complex systems and biomedical applications, and providing professional training and consulting services based on his over 20 years of experience in academic and the industrial experiences. So he does all that, and he works for us and helps us out as well. So we are very pleased to have you. And with that, I'm going to pass it over to you. Thanks so much. Go ahead.
Okay. Thank you, Collins. Thank you for your introduction. Okay, I'm Min Jelin. I'm in Seoul right now. So today I'm going to introduce one of our research topic. This is it's called 3D CFD peak simulation of a dielectric loaded rectangular waveguide for terahertz wave generation. This is under collaboration with Dr. David Smith at the TWSS in the past several years. Okay. So first of all, I would like to acknowledge the support from TWSS, and also David's project is funded by US DOD and DARPA SBIR program, and also support from Hanyang University. So this is the outline of my talk today. So first of all, I would like to introduce some background and our motivations. Then I will give you some field analysis of these simple components for terahertz wave generation. And then I will show you some model designs developed in Vcim, and you can use this to carry out 3D CFD peak simulation results. And then finally, a conclusion remarks. So as well known, all the EM wave spectrum cover a lot of applications. Here, just give you a brief impression of we human beings would like to have a lot of applications based on this electromagnetic spectrum. Luckily, we have Vcim, such tool to perform all the EM and plasma related simulations for most of these applications. So you can simulate what you want. So if you come out with ideas, you can realize it. So what I want to emphasize here is terahertz. So as we know, in the past decades, we developed a different kind of EM source, from radio, microwave, up to laser, X-ray, or gamma ray. So we are in short of terahertz source in past maybe 2 or 3 decades. We really tried very hard to realize this terahertz source, but compared to other frequency range, terahertz source is still lacking. So we know terahertz, by definition, this is electromagnetic radiation in frequency extending from 0.1 to 10 terahertz. In terms of wavelengths, is from 3 millimeter down to 0.03 millimeter. So terahertz wave have been used to characterize the electronic, vibrational, and compositional properties of solid, liquid, and gas phase materials during past decade. So many rotational and vibrational spectra of various liquid and gas molecules lie within terahertz frequency band. and their unique resonance lines in terahertz wave spectrum allow us to identify their molecular structures. More and more application in imaging science and technology call for well development of terahertz wave source. So this is a well-known example for terahertz imaging. So we can see this weapon concealed. This cannot be detected by other sources. So as well known, we have mainly two ways to generate EM waves. One is based on quantum mechanics, is laser based. And we know that because it's based on light quantum, so if we move to longer wavelengths, we have lower energy, we have lower power. On the other hand, we have traditional vacuum tubes, or we call it microwave tubes, or today we call vacuum electron devices. So like Andy introduced, we have conventional microwave tubes like a magnetron. So however, because of frequency increase, the size will be reduced correspondingly. Then we also lose power. So this is a well-known terahertz gap in nature or in the limitation of our human technology. Luckily, we have gyrotrons. So I did spend some years in researching gyrotrons. It can barely fill this gap, but we still have a gap. We call it a millimeter or submillimeter wave gaps, or simply terahertz wave gap. And one of the big motivation of this work is from working with Dr. David Smith at TechX. So he has an interesting project. We were trying to use semiconductor device to provide the electron beam. And David told me, oh, we need some kind of slow wave structure. So I am trying to came up with different types of slow wave structure. One of that is what I introduced today. So this structure was studied for decades. So this is a paper published about 20 years ago by Argonne National Lab. So these researchers did a great work in field analysis of this dielectric loaded rectangle waveguide, but they focus on accelerating structure. So their main focus is next generation linear accelerator. They are looking for high gradient linear accelerator. But we know that reverse accelerating structure can also be a decelerating structure. So it depends on the phase or synchronization of electron beam and your wave structure. So we would like to ask a question. So field analysis of dielectric loaded rectangular waveguide is possible for a decelerating structure. Then it's equivalent to a wave generator. Okay, so this is our idea. We came out. Can we reverse this accelerator structure to become a wave generator? So here we are trying to use Vcim to realize this idea. So some background. So as we know, here we use a method called FDTD peak simulation. And I added one word called conformal. I will introduce this in just a minute. So this is a peak method mainly introduced half century ago. So we know we have a very solid foundation for this numerical method. So this shows you a peak loop, very well known. So basically we solve particles. We check particles in a Lagrangian frame, and we solve basically mass wave equations in EM on all Eulerian mesh points. So we know one is the continuous space, the other one is discrete space. So we do need the interpolation. So we require two interpolation. So we have this information exchange between particles and the fields on grid. Okay, so if you understand this loop, then you can do big simulations. You have more confidence. And a lot of following talks will focus on this multicolor collision. This is another module, and to make this method even powerful, and for simulating plasma discharges. So for conformal FDTD or simply CFDTD, I name it, is because in Vsim we have locally conformal grids, or we call it cut cells from Magnetron algorithms. So here, assume this top left-hand corner is metal, and inside this circle is vacuum. So we have this curved boundary, metallic boundary. And for this, for traditional FDTD, we have stair step, and you will lose accuracy. So we know that for E cell, we may have second order accuracy for rectangular geometries. However, for curved structure, you may have only first order. But by using this cut cell, we perform integration on this cut cell, then we can retain second order accuracy at least. And this is a detailed algorithm for FDTD. So for Faraday law, we have this field updaters. Okay, we have, and for Ampere law, we keep it the same. So for Faraday law, we have to carefully update by integration this cut cell. We have performed contour along this path. So it's a path integral. You can consider it's a path integral. So if you want to understand more detail about this algorithm, you can look for this paper published maybe, okay, it's like 25 years ago. Okay, so this algorithm is well implemented in Vsim. So we know Vsim is a versatile simulation package for EM and plasma modeling. So this is a tool we used in this work. And it's well known that maybe in past 10 years, Vsim, we call it a Vcmpd before, right now called Vsim VE. So for Vsim for simulating micro device, the framework has mainly been built several years ago. So we can successfully model many devices like a Smith Purcell radiation, and the Magnetron, and the Vcm array, Gyrotron, and the TWSS Electron, and the other vacuum electronic devices. So last year, I also gave a talk on Magnetron. We try to optimize the field emission-based rising sun Magnetron by using a 2D CFDTD pick, and we successfully get a design for industrial application. So we reach about 80% by using this optimization. So for field analysis here, we have field analysis. We took this from this paper. So this paper did a great job. They use the model matching method, so they have a lot of analytical formulas. Okay, so in Vsim we have a good advantage. One of good advantages is we can use this formula. So if you can find the formulas, we can excite formulas in for your wave generator in the structure. Okay, so this is dielectric field waveguide. And it's well known that in traditional waveguide, we have fundamental mode TE10, and then we have other higher mode TE11 or TM modes. However, if we introduce dielectrics, we will have hybrid modes. Okay, so there's no longer TE or TM modes. So we have what we call LSM mode, or it stands for longitudinal section magnetic, and the other one is called LSE modes. So these are normal modes in this kind of structure. So this is very different from traditional waveguide. So this is the first thing I have to mention. But luckily, these researchers, they give detailed field analysis. So if we want to study this structure, this spiral wave structure, we can mainly excite this component. Okay. So you might ask why I know we have to excite these components. If you work with waveguide for decades, you will have this experience to know which component you should excite. So for LSE MN mode, we excite by using H function. So here for LSM, we use EY component. Okay, so we know in order to understand the slow wave structure, dispersion relations are very important. So this is model matching method given by these researchers can give us a ideal dispersion relation. Okay, so we have closed form for this, and this can be carried out by any CS. So here shows you the dispersion determined by this closed form. So as you can see, for example, we have this light speed line, and then we have this LSM11. But this dispersion curve is rotated by 90 degrees. So maybe it's not like what you see in many vacuum electronics literature. But this is their illustration in maybe accelerator community. So they propose to use LS11 mode, and they use two waveguide to generate a uniform field. So this wave field can accelerate, they can generate a high gradient field to accelerate particles. Okay, and in recent years, there are other groups in UK. They try to study electron terahertz interaction in this structure, in similar structure. So their goal is try to use terahertz wave to manipulate the electron beam. Actually, is to get a diffraction. So they use the LSM01 mode to achieve this goal. And here I show you the model design. So with this configuration, we can have two kinds of beam. So one is a traditional pencil beam, like the one shown on the top figure. And the other one is a sheet beam. So interestingly, I worked with David 20 years ago at the SLAG, maybe, yeah, more than 20 years ago at the SLAG on sheet beam Klystron for next, for next linear collider. So actually the project is kind of sheet beam, but it's in solid state. So actually Vcm is multi-physics software. So internally, Vcm is able to simulate a solid state device, but it's not released yet. Okay. But here I propose to use this structure for vacuum electronics. So this is real electron beam. This is not the inside semiconductor. But in David's project, I propose to use this structure for his semiconductor electrons to 2D electron gas to deck. Okay, the geometry, the cross section I used, this is referenced from another work in terahertz device. That's a 40 waveguide terahertz generator. So I use this cross section as my waveguide structure. So it's 380 micrometer by 190 micron in cross section. So it's very easy to create a model like this. So this is a simple rectangular waveguide, and then you can use Kata to generate this simple structure. Okay, so this is so we want to make this more realistic. So we try to try to find some reference which will give us some dielectric function, some realistic material in terahertz frequency. So this is the parameter we used for this dielectric in the model. Okay, as I said, these researchers in UK, they already started the experiments. Their goal is to use terahertz to they use terahertz electron beam interaction to deflect the electrons. Okay, this shows their experimental setup. So with launching of terahertz wave, they couple this wave into this dielectric lined waveguide or dielectric loaded waveguide to deflect the beam, to deflect the electron beam. And then they have different design for this. They call dielectric lined waveguide. Okay, I call it a dielectric loaded waveguide. Okay, and here we have to add this dielectric material. So it's also very easy in Vcim. And then launcher beam. So here we use a pencil beam, and the energy is about 1.8 kilo electron volt. And with a strong confined magnetic field at 1 Tesla for beam forecasting. And before we do the hard test by introducing these particles, we have to make sure Vcim did a good job in this slow wave structure, in characterizing these slow wave structures. So this is a traditional waveguide. So as you know, we have fundamental mode TE10. So this is like a trivial work. So I did this benchmark to show, okay, Vcim can solve waveguide dispersion, of course. This is TE10 mode. So the symbols represent Vcim results. And this is TM11 mode in a waveguide like this. So this dispersion agreed with the analytical form very well. However, for this dielectric loaded waveguide, to determine dispersion is not trivial. So we need to use a wideband excitation signal to determine the dispersion relation. So I use Mathematica to generate a pulse, and this pulse represents a wideband signal. So on the right-hand side, you can see the FFT of this signal. It covers frequency from 0 to terahertz. So this is the frequency range we are interested in. Okay, and this function, this time-dependent function or signal, if you know the function form, you can implement this easily in Vcim. Okay, so we can excite exactly the same signal in FTD peak simulations. Okay, so this shows you the wideband excitation. So we excite this wideband in this excitation, but remember I told you you have to pick field components. So for LS, if you want to study LSE or LSM, you should choose different components to excite the wave. So here I focus on LSM. And as you can see, there are a lot of normal modes excited. Okay, but we are interested only in certain modes. There are a lot of higher order modes, as we know, but we are interested in LS11 mode specifically. So how can we get a later mode? So in Vsim, we have a very good analyzer. So this was developed by Dr. John Carey and Craig Warner. They invented a method from linear algebra. So in time domain, we can get these eigenmodes. So this is field diagonalizations. We can get this eigenvalue and the corresponding maybe Q value, and also field patterns like this. Okay, so we can locate this eigenmode by this diagonalization method. So we can, this shows you different mode patterns. Okay, then we can, with this information, we can get these eigenvalues. Okay, we can plot. So we have, so this is not available in Vsim. You have to do this manually. So after you got this eigenmode, you have to measure the wavelengths. So you can get this symbols. This is for Vsim simulation. And as you can see, it agree with this dispersion well. Okay. So we verify that okay, we can get the LSM11 mode from this co-test simulations. And then the good thing of using Vsim for vacuum electronic device study is that you can use the same grid. After we perform co-test simulation, with the same grid, we can apply. We can continue to study hot test simulations. Okay, so we can use exactly the same setting, the same grid, but just launch the beam for a study. And then here I use the 200,000 microparticles, and the grid size is given here. Is 50 by 25 by 500 because it's quite long. So we want to see the electron beam and the terahertz wave interaction along this waveguide. Okay, so first we started with the signal turn on. So we have terahertz wave excited in co-test simulations, and just launch the beam together. So you can see this electron beam, of course, will be modulated by this terahertz signal we excited. So this shows you the phase plot in x direction. So this is ux versus x. This give you the phase information. So in the transverse direction. So we have uy versus x and uz versus x. So you can see longitudinal bunching and this is transverse bunctions. And this also demonstrates you that actually why we want to use LSM11 mode, because it's symmetric in transverse direction. This is very good for wave generator. Okay, for this hot test simulation, we can study how these electrons are modulated. So this is for diagonalization of electron beam. So we plot this particle. This is a current emitter from cathode, showing in blue, and this is collector current at the end, showing in red. And after doing FFT, you can see these particles carry these signals. So it's similar to what Andy did. We can get some information from these particles. This is another trick for you. So, but this is in frequency domain because we are interested in these terahertz signals. So as you can see, because we excite the wideband, so a lot of normal modes interact with these electrons. So for many frequency, we can see these signals were amplified. So you can see this radar signal, these peaks come out of this blue signals. This demonstrates the modulation of electron beam by terahertz signal. But this is not our purpose. We are not making an amplifier. Here, our goal is to make a wave generator because terahertz source is very expensive. It's harder to get. If you can get a terahertz source, then you can be rich. Okay, so our goal is to make a terahertz generator. So let's turn off the signal in this case. So this is the case when we turn off the wideband excitation. So this is purely no signal simulation. So we don't have any seeding here, but you can still see this bunching. So you see these electrons are bunched. So in phase space, we can see this clearly. We still keep this longitudinal bunching without any seeding. So this is from actually we call vacuum noise. It's like a magnetron. So this is the trick in vacuum electronic devices study. Okay, so we can still study the similar. We can see that we can use a similar analysis to catch the physics. So again, we observe this frequency spectrum of this emitted current and the deposited current. You can still see this signal generated. So these electrons carry these terahertz signals. And we can consider these are wave generator. So this electron beam carry this signal can get this, we can get this source terahertz signal amplified. Actually, this right now it's not amplified. It's noise amplified, but this is source generated. So we have terahertz source. And however, this is wideband because we launch this electron beam. If we didn't tune this beam carefully, we can excite many modes. So this shows maybe two groups of terahertz wave will interact with this electron beam at this 1.8 kilo electron volt. So this is the last result that I have. So this is EM waves. So we can observe electric field on the, this is on the axis, certain location. You can measure this electric field and you can perform this FFT. So this gives you the terahertz spectrum. This is from 0 to about 2.5 terahertz. So we do see this wideband generation. And so here we have wideband terahertz source, and but the power is not well categorized yet. So this is like a preliminary results. So further study is continued. So finally, summary. So in this work, we propose to use partially filled rectangular waveguide, or we call it a dielectric loaded waveguide, as a slow wave structure for terahertz wave generation. This is a reversed acceleration in terms of the proposed accelerator structure, since the beam wave intention can be employed. So we know a lot of design accelerator community can be borrowed to serve our purpose. Field analysis of this slow wave structure is conducted using 3D conformal finite difference time domain method, and the corresponding dispersion of TE, TM, LSE, LSM modes are calculated and include agreement with analytical theory. The beam wave interaction for TWSS wave generation studied using 3D CFDD peak simulations, and we demonstrated that terahertz electron interaction can be observed, while more investigation is needed to obtain a meaningful gain or oscillations. I think that's all. Thank you very much for your attention. I'm here for taking questions.
Thank you so much, Ming-Che, for that presentation. Now that it's middle of the night officially for you. So it looks like we have a question in the Q&A, which just says, I believe this is for your presentation. For the waveguide, does the case A equal B then recover the usual TM and TE modes?
No, because traditional TM and TE mode, this is require vacuum or totally filled dielectric in this waveguide. So this you can imagine this dielectric material break the symmetry. So this fundamental TM and TE modes are no longer exist in. Actually, they are coupled. Okay. So because they have to fit the boundary condition between vacuum and the dielectric. So TM and TE modes cannot fit in this structure. Okay.
Thank you. If you have questions, you can type them. There is a Q&A box on the bottom of the screen. Just type that in there and I can ask that for Ming-Che. So we have our next presentation coming up in about 20 minutes, and that'll be Dr. Tom Jenkins.
Okay.
And then we will have 3 more presentations tomorrow. We've got our exciting magnetron sputtering one that we're all interested in hearing. That'll be presented by Dr. Daniel Main. And the full schedule is on our website if you need to see the selection of talks.
So maybe I can explain this in more detail. So for this traditional for this vacuum waveguide, we have this TM modes. So usually we use TM mode to characterize this structure, but this is a faster wave structure actually. So you know, if we don't have any material, then the phase velocity in this waveguide, traditional waveguide, is faster than speed of light. So this waveguide cannot be used as a slow wave structure for our purpose. So that's why we introduce this dielectric material. As we know, EM wave in material, inside material, propagate slowly, slower than speed of light. So you can imagine some wave live in vacuum, some wave live in dielectric. Then in average, the speed will be slowed down to be less than c. Then in this case, our electron can catch up this slow wave to be synchronized and get a EM wave interaction with electrons. Okay.
Thank you. We have and kind of a clarifying question. If A equals B, doesn't that mean that the waveguide is built?
A equal B. Okay, I see. You mean it's a totally filled, or I think my parameter defined maybe. Okay, let me make sure if maybe I think I think A and B is corresponding to width and height, and we use D to. Oh, okay. Here I use A and B. Sorry. Then you are right. If A is equal to B, then it's totally vacuum. Or if A is 0, then you have totally field waveguide. Then you can recover. Yes, you can recover TE and TM modes. Okay. So I'm sorry, I misunderstood the question.
Oh, that's okay. It's always a challenge here. We have another question that says, is the dielectric material frequency independent?
Actually, actually in reality is no, but this is very complicated. But this can be implemented in Vcm as well. But for preliminary study, we assume it's a constant within this frequency range. But you are right. Actually, dielectric material is frequency dependent. We have you can look for dispersion of this material, but you know, in terahertz frequency range, studies are very few, because for especially for characterizing these materials, because terahertz source is expensive, and to determine dielectric function is even more expensive. Experiments. So there are very few studies. So the reference I found is just for certain frequency. Okay.
Sure. Let's see if we have any final questions. Anyone before we let Ming Che go to bed at almost 2 in the morning in Korea. So we're so pleased though, again.
No, that's okay. I will attend next talk.
Oh, I know you will. It's always
I'm interested in science and the Vcm and
yes.
and its applications.
All right. One more round. So questions. Also, as you VSIM 12 was released this week. I keep getting questions on when it's going to be available. I'm hoping today, but possibly. I just want to say by the end of the week, we will have evaluations out. Please, when a release is coming with the same week as our conference, it's just a lot, but we'll get those out to you. We want to make sure that everybody who wants to try out the new release has a chance to do so. Even if you're a current, especially if you're a current VSIM user, we want to get that too. So, all right, Ming Che, I don't see any other questions. So I think that we can let you go for today. Thank you so very much.
Okay. Okay. Thank you.
Thank you. And if everyone else can just wait, we will start up again at 11 a.m. Mountain Time in about 17 minutes. Hello and welcome back to TWSS 2022. My name is Colleen. I am the sales coordinator here at TechX. Thank you so much for joining us today as we are on our third presentation for today. It's almost our last one. We do have one tonight at 7 p.m., but that is a repeat of the one we had this morning. With me today is Dr. Tom Jenkins, who is going to be talking to us about using Vcim, as you can see, to model low temperature gas discharges. Dr. Jenkins is a senior research scientist here at TechX. He specializes in the theory and computational modeling of RF and magnetohydrodynamic phenomena in plasmas. He is a developer for the Vcim code, a past developer of the Nimron code, and an experienced user of high-performance computing platforms at OLCF and NERSC. Throughout the past several years, he's worked collaboratively with members of the RF SIDAC team to model nonlinear wave phenomena, impurity reduction, and sheath physics associated with RF antennas. In addition, he has published research on various noise reducing and speed limiting algorithms for faster and more accurate nonlinear plasma, particle, and cell modeling. So welcome, Tom. How are you?
Doing well, thank you.
All right. I will leave and pass it on to you.
All right, and you can hear me and you can see my screen, I presume, at this point?
Yep, everything looks good.
All right. Okay, so I will be talking today about our work to model low temperature plasma discharges with Vcim. I want to thank collaborators on the Vcim and the Vcim examples and composer teams, and a couple of folks up the hill at CU Boulder as well in the Center for Integrated Plasma Studies. We'll be talking about some work we've published together in this context. And just overall things I want to go over in this talk, I'll be talking about Townsend discharge physics and one of our new examples and our parameter scan feature, which you've probably heard about previously in some of the talks, but it's a good feature, so it's worth mentioning again. I'll be talking also about neutral gas breakdown and computing Paschen curves using Vcim, which is our recent publication with CU. Some words about the physics of kinetic collisions more generally, and some work on our with Vcim to model RF-driven capacitively coupled plasma discharges as well. And just generally speaking, these all fall under the umbrella of the Vcmpd, Vcim for Plasma Discharges package. And that's kind of where I come at this from. So Townsend discharges, this is kind of basic stuff, but that's where I'll start. Now this Townsend discharge happens with, we have a parallel plate geometry. We fill in between the plates, we fill the space with the neutral gas, and then we impose a fixed electric field between the plates. We've essentially set a constant potential difference between those two plates. And we pose the question, can this gas carry electric current? And if so, is it interesting? So you can imagine if you were to, before I do anything dramatic here, if we were to just let an electron go from the cathode, it would run up the electric field and hit the anode, and we'd have a current. Real life is a little more complicated than that, of course, and so as we emit an electron from the cathode, it will accelerate, and if it gets sufficiently energized, we'll hit a neutral atom and ionize it, and then we have 2 electrons and an ion, which means that pretty quick we have 4 electrons and more ions and so on. We get an avalanche, essentially. Every ionization event produces a new pair of electron-ion pair, and the electrons do just what the old one was doing. They keep running up the field to the anode. And the ions accelerate downward toward the cathode, although much less responsively because they're heavier and thus less mobile. When they get to the cathode, they hit it, and maybe they produce secondary electrons, which starts the cycle all over again. And essentially what we get is an amplification of this, whatever initial current we put out. There's some amplification having to do with the production of plasma through ionization. And so you also have other collisional processes that will affect the discharge physics. I'll talk about those on the next slide. And there's an underlying assumption here that we never get quite enough charge to modify the electric field. So that's just imposed and such. And sometimes we forget about the secondary emission as well and just concentrate on the ionization process itself. But Townsend summed this all up in this equation here, which is the ratio of current that you actually get to the current you started with is some complicated function of the ionization mean free path x naught, and then these Townsend coefficients alpha and gamma, which have to do respectively with how many ionization events we make per unit length and how many electrons do we make when we hit the cathode. So we can look at this in Vcim. I'm going to first talk briefly about collisions. What do the other collisions in this discharge do? So we have, along with ionization, we might have excitation collisions where an electron comes and kicks one of the electrons in a neutral atom up to a higher state, but doesn't dislodge it all the way. This is essentially a sink of energy and momentum. And we expect that to reduce the overall ionization because we're taking energy out of the electrons before they get fast enough to be ionizing. We might also have elastic collisions, either of electrons or ions with the neutral gas. And this essentially is a redirection or a diffusion of the momentum. And you can think of this, in elastic collision, we don't lose energy, but we kind of redistribute the momentum into other components perpendicular to the field. And so we're able to get to a higher particle energy overall. And we expect that to, depending on the cross-section energy dependence, that may increase or that may reduce the ionization, depending where we are on these curves over here. These are cross-section curves for various reactions we might see in helium, elastic, or excitation, ionization collisions and such. And for the ions, we have charge exchange, backscattering type processes. And this again is a sink of energy and momentum. And instead of affecting the ionization directly, that may affect the secondary electron emission. If we go to a higher energy or lower energy state, do we get fewer electrons when we hit the cathode, or do we get more of them? So there's some dependence there. In Vcim, there's a bit of technical issue, in that how do we measure currents? Well, we have these particle histories that you probably know about if you're a Vcim user, but what current do we expect? Here, if we have an electron running up the field and hitting the anode, we'll call that 1 unit of downward current, if you will, because of the sign of the electron being negative, we'll flip the direction. If we have an ion that hits the cathode, we'll also call that a unit of downward current, and so that's another +1. So essentially, if I kick off some number of electrons from the cathode, I expect to get at least that many at the anode. But in addition to that, I expect 2 more current units for every ionization event. And we make a pair, and then the electron comes up here as well, and the ion comes down. So that's +2. And then to get even more complicated, if I have an ion comes down, hit the cathode, and kicks off some number of electrons, as they come off, they leave behind that equivalent number of ions. And so I have M+1 ions coming in, and then I have M free electrons that are going to run up the field later. So the bookkeeping gets a little bit complex. And you can tell that by my font size here, that if I'm going to do the complex case, I put it really small at the bottom. And in the simpler case that our example covers at the moment, we're just going to neglect secondary emission entirely. We'll cross off this denominator essentially and try and compute this alpha coefficient using Vcim. Essentially what we'll do then is we will spit out some number of electrons from the cathode, and then we'll catch them at the anode and count how many actually got there. Generally speaking, we'll catch more than we spit out, and that will have to do with the ionization. And So the difference of those two numbers is the number of ionization events that occurred. And we double that to get the total current. So this is the ionization current, 2m minus n. This is the initial current n. We add them together and divide by the unamplified current to get this ratio on the left of our equation. And it simplifies a bit, of course. I was going to mention to count particles, we can just do particle history, which uses this menu in the visual setup. And then whatever result you get, you can just multiply by dt over q, and that will give you a particle count. Experimentally, if you were to go and compute the Townsend coefficients, you would do something like was done in this paper in 1964. You fix the electric field essentially, and then change the voltage and the plate separation concurrently so as to maintain that fixed electric field. And then you just do a scan in voltage, and then you look at the current that you get for various values of the pressure and of the field. So you can imagine this would be a perfect thing to be able to replicate in simulation, because we can just run a simulation, run another one, run another one, run another one. Nobody wants to do that manually. And so we have developed our new scan feature, which we hope you will find useful. When I've set this example up in the visual setup under the constants menu, I've set this voltage difference. And then I've set up the input file so that, as we vary that voltage difference, we also vary the distance between the plates automatically so that we maintain a fixed electric field. So that distance comes in under the parameters. It's functionally dependent on this voltage difference, whatever I've set that to be. So that's all standard setup stuff that you're probably familiar with if you're a Vsim user. What's new is under our design tab, which comes in on the left under the run tab, we can then take this voltage difference parameter, we can select it as a parameter over which we're going to scan, and we can list the values that we want it to take in that scan. Here I've listed 7 values, and so I'm going to essentially do 7 runs on this plot. And with one single click, Vsim will set up those different runs in a subdirectory. It will do all the pre-processing, which is dictated in this column or these columns, and then it will sequentially or in parallel, depending on your system. You can choose that down here. It will run all of the simulations that you've asked it to in the scan. We have also, for this particular Townsend case, built an analyzer that will look over all of the output from the scan. So this is the scan analyzer Townsend.py, which will show up in your list of analyzers in the tab. And so we can tell it our scan name, our electric field, how many runs were in the scan and what we were scanning over and such. And then we can go in and compute from that. From the aggregated scan data, we can compute the Townsend coefficient. Essentially what we're doing is we're fitting an exponential to this curve and seeing what parameter best characterizes that exponential growth. And when we do that, we get quite good agreement with the data that's presented in this 1964 paper. The alpha being the Townsend coefficient divided by P naught, the pressure, comes in at 1.3, just as is predicted in the paper. So if you end up using this scan feature, and obviously you probably won't be doing this problem, but if there are use cases that are of interest to you, that you'd like an analyzer for a scan that does this thing or does that thing, that would be a thing we'd be interested in discussing. We'd like to make this scan feature and the associated analyzers more useful. So do reach out to us if that seems like a relevant thing that we could help you with. Going to change direction slightly. I'm going to talk about Townsend Paschen curves now. And this is essentially a curve that tells you where these breakdown thresholds for Townsend discharges happen. You can imagine if I had a very weak voltage and I sent an electron from the cathode to the anode, then nothing would happen, and we would not call that a plasma. But if I had a very strong voltage, you can imagine this avalanching, and there would be a breakdown and things would be more interesting. These Paschen curves, what they do is they tell you where that interesting physics is going to start, setting a threshold for where the breakdown will occur. So it's the same flavor of simulation. We have a parallel plate geometry, we have a separation distance, and we have a neutral gas filling the gap between the plates. And here we're going to vary the electric field strength and then compute the associated voltage that goes with that. What is found by Paschen is that the breakdown voltage depends on the product of the pressure and the plate separation, so P times D. And we want to figure out using Vcim where this breakdown threshold occurs. And this is clearly of interest. You can think of many situations where you would not want a avalanche breakdown type thing. If you have a grain elevator or something, that's bad. The spark sets everything on fire. And the physics of this discharge is, and of this curve shape, if P times D is too low, then essentially we have a small simulation. And if you have a small simulation and a large ionization mean free path, you don't get any ionization. Particles leave before they can do anything interesting. So unless you crank the voltage really high, you don't get a breakdown. Going over to the other side, if P times D is very high, that means high pressure, lots of background gas, your non-ionization mean free path is very short, and your electrons keep bumping into things before they can get up to the ionization energy unless you kick the voltage very high again. So it's high on the right, it's high on the left, and in the middle it comes down and hits a minimum that's dependent on the gas properties. And it turns out it's also slightly dependent on the material surface. You can have secondary emission coming off of your plates, and depending what the plates are made of, that will affect the shape of this curve. So here's the Paschen curve, essentially. This is from a paper by Phelps, and he's computing these curves for argon, but for lots of different metallic surfaces of the plates. Are they clean? Are they dirty? And so on and so forth. And you can see there's a fair bit of variation in the data depending on what your plates are made of and so on. Likewise, if you look at secondary electron yields, depending on the energy at which an electron hits the plate or an ion hits the plate, you may change the probability of emitting an electron out. And that's kind of encapsulated in these plots here. And these are plots that we have fit to piecewise linear functions and then pulled into Vcim to do our study of Paschen curves. That study is covered in this paper, which was published last year. This is Joe Tice, who's a graduate student up the hill at CU. And we were able to use Vcim to look at argon Paschen curves, and we were able to successfully compute those curves and get good agreement with experimental data. So these discharges have lots of collisions, elastic, and multiple excitation processes. We get ionization, and then, as I said, we've got energy-dependent secondary electron emission when the ions hit the cathode. From the title, you might deduce that we're also doing something clever with our particle simulation. We have a new method called speed-limited particle in cell, which is a feature we're developing in Vcim, and we've put some of the basic functionality in Vcim 12. It's not extensive at this point. We do not want to give you too much rope so that you can hang yourself with, as it were, but we want to put the basic functionality in and have people who are interested test it out. See if it's relevant to your discharges. Just give you a one slide summary of what speed limited pick is. Essentially, if you have a discharge where the ion physics is interesting and where you need kinetic electrons, that becomes problematic because your electrons are particles and they limit your time step because you have to resolve the electron motion, the plasma oscillations and such. And very often that physics is not interesting to you. You just care about what the slow ion distribution is doing if you run it for 100 microseconds or something. And you don't want to resolve electron dynamics on those time scales. So in SLPEC, what we do is we slow down those electrons. We make a rule that says they cannot exceed a certain speed, and we put on a threshold, a speed limit. We choose that threshold so that the only important electrons are the ones that are moving slower than that. Those will just follow conventional pick dynamics. And then the ones that are faster than that will just do whatever they do. And hopefully it's not very interesting. And because we have slowed down the fastest electrons, we are able to take larger time steps and we're able to get much faster run times, order tens to hundreds of times faster than we would get from conventional pick. There are caveats here. You say 10 to 100 times faster and everybody wants to do it right away. But this is best for unmagnetized electrostatic plasmas where you care about the ion physics primarily, but where you have kinetic electrons in order to capture some kinetic physics that you want, maybe a non-equilibrium electron distribution or absorption or something. The work group up at CU is working to generalize the applicability of speed limited pick, and we will see more publications on that as that work goes forward. But for the moment, this is what it's good for. And I've got a couple references here you can look at, and I'd be happy to take questions about it offline or in the future if this feels like a thing you'd want. But going back to Paschen curves, these simulations where we decide did the plasma break down or not have to be run for a long time. Now, if you're above the breakdown threshold by a lot, and then you run the plasma, you run the discharge, and you start with 1,000 particles, and pretty quick you have 10,000, and sure, you got breakdown. If you're below the breakdown threshold, you start with 1,000 particles, and pretty quick you have 0, and yeah, you definitely did not break down. And if you're right on the border, you're going to have to run a long time before you know if you're getting gradually more, or gradually less, gradually less. And so these simulations are very demanding computationally. You know, clearly the mass ratio of electron to argon is going to be problematic for your dynamics if you're trying to look at the argon physics. So we use speed limited pick to bring that ratio down a bit. And this is the result. In green, we have experimental data from Phelps. There's the paper I showed earlier. And then in red, we have standard pick in VSIM. And then in blue, we have speed limited pick. The agreement's quite good, especially at high PD. Should point out that these simulations out here are definitely not ones you'd want to do with conventional pick because they would take you of order weeks to months. With the speed limit, we can speed that up by factors of tens or hundreds, and that makes things a good deal easier. Down here at the lower values of PD, we can simulate with both pick and SLPEC, and we get good agreement between the methods. We don't get quite as good of agreement with the experimental data, but you can see there's quite a bit of variation in that as well, and having to do with the metallic surface composition and such. But we feel pretty good about this, and it's a good demonstration of our new algorithm as well. From there, I wanted to mention, some of you have probably seen me talk about this before, we can also model RF discharges with the Vcmpd package. This movie that I'll show you is a discharge posed by Miles Turner. And this essentially is a simulation benchmark suite that he's proposed in this paper. And pause the movie here for a second. What you see here, this plot is kind of busy, but I've got a mean density of electrons in red, ions in blue in this discharge. This is a one-dimensional discharge, and so I essentially two capacitor plates with a plasma in between, and I'm going to drive that plasma with RF on one of the plates. So I get current on the left, I get current on the right from the two species. You can see the potential down in the bottom here, and then the profile of ions in blue and electrons in red. And then this is the phase space, which I've done some rescaling on to make everything visible. Now you can see in the phase space, the electrons kind of slosh back and forth. They move left and they move right. And as they move to the right, or as they move to the left here, you can see there's a big electron current spike when they hit the wall. Then they're going to go right, and we'll get a big electron current spike on the right. You can see that the electron discharge density kind of flops back and forth in the red here. Well, the ion density is pretty steady, since the ions are not quite as responsive to the RF field. And you can also see these filamentary structures coming in. As the electrons retreat, we have this sheath that forms, and so we do a bunch of ionization where the electrons are. We create a bunch of ions, then the electrons move away, and those ions fall down the sheath, and you can see the filaments coming down the sheath and coming down the other sheath on the other side. And you might envision catching these particles with an absorber and looking at their incident energy and what is the ratio of V normal to V perp, and what is the energy distribution and such. And you can do all kinds of interesting looks at the distribution in that way. Where'd my slideshow button go? Okay. So in this discharge, we have multiple flavors of collision, same as we had in the earlier Position discharges in Townsend. And what these discharges are really designed for is model benchmarking. The solutions that you get in steady state are very sensitive to the details of these collision processes and whether you're getting all the little bits of physics right that comprise those processes. So it makes for a very nice test suite. We've employed for nearly a decade now. We've had quite good agreement with each of the benchmarks. And by quite good, I've illustrated that over here on the right. This blue curve is Turner's prediction for the density, and then on the red is what we're getting, which looks pretty nice to me. Down below, I've plotted the time averaged electron energy distribution function for a couple of the cases. Now, Turner's data is in the triangles, and then Vcim data is in the colored dots, green and cyan. And the agreement's quite good. Statistically, to match Turner's benchmark, there's some extra work that needs to be done. Some of the assumptions made by Turner are not quite physical. For example, the partitioning of energy in an ionization collision, how much energy goes to the ion, how much energy goes to the two electrons, how's that distributed and such. Vcim has quite a complicated model for that coming out of the plasma literature. And for Turner, it's essentially a very crude division of labor, if you will, and we would need to write a brand new collision process and then run with that. And the only physics in that collision process is that it matches Turner's way of doing things and allows us to meet the benchmark in a statistically rigorous way. So we're doing that, but that will probably not be consequential for your problem. But we do plan in Vcim 12.1 to put out some more details on that work and to verify that we are indeed rigorously matching these benchmarks and capturing the physics of low temperature discharges in the way that one might wish for. So generally speaking, we have been working with our Vcmpd package. We feel good about our efforts to model physics that matches experiments. We got good agreement with Townsend discharges, good agreement with Paschen curves. We're doing good work in developing good analyzers for modeling RF-driven low temperature discharges, capacitively coupled plasmas, and then, as will be talked about in a talk tomorrow by Daniel Main, we're developing our capability for magnetron sputtering that brings in many of these features as well. Together with that, we've got a new parameter scan feature, which we hope will find you that you will find useful. And if you have suggestions for how we can make that better, we will try to pay good attention to those. And we continue to develop good particle and cell algorithms as well to give faster performance and simulation speed up and to capture the physics of your problem in a way that's computationally tenable. So it's basically all I've got. I'm going to put these slides up on my website, which I've linked here, if you'd like to download them, and if you'd like to reach out and talk about speed limited pick or about any of these other discharges, be happy to do that later, but I'll also take questions now. So, thank you.
Well, thank you so much, Tom, for your presentation. So it looks like we have two questions that have been submitted from the audience. The first question is, how does the Paschen model change when the ionization rate coefficient depends upon E over N?
Well, that would just be, I think, a different scan, right? You could envision doing one scan for a particular E over N, and then you would need to do another one for a different value. And I guess that's kind of captured here, right? In this plot from the 1964 paper, they're changing E, and so you get a different value. You would need to do a different scan to capture that physics, but it's essentially taking our 2D Paschen curve and projecting it into a third dimension as you vary that parameter.
Okay. Did the simulations include metastable states for argon?
Let's see. Don't actually remember that. For the Paschen, I don't think so. That's certainly a thing you could add. And then you would, of course, need to add all the collision processes associated with the metastable states, and the cross sections are different. And you could certainly do a more detailed look at that and what physics that brought in, and all the capability to do that is in VSIM already. So you just need the cross sections and putting in all the reactions that you wanted. So that could certainly be done.
Very good. If anyone has any questions, there is a Q&A box on the bottom of your screen, and you can type it in there while we still have Tom available. We do have another day of TWSS tomorrow. We've got 3 different presentations. We have an introductory presentation that's at 9 a.m. And that is actually more for if you've never worked with VSIM and you are just interested in a general overview and you want more general information than all of the detail we are presenting here. So that one will be at 9 a.m. Mountain Time. After that, then we have Magnetron Sputtering by Dr. Daniel Main, this is the new example that we have in VSIM 12 that we are very excited about, because it's something that we are getting a lot of requests for, and we know that it's an important simulation to be able to do. And then we will have one more from Dr. David Smith to finish out the event. So any other questions before we end? We also released VSIM 12 this week, so or are releasing it. I guess I should say it should be available possibly by today, possibly by tomorrow. And we will get that out so that everyone can try some of these new features that we have been discussing as well. All right. That might be it, Tom, for today. So I really appreciate you taking the time to go through all of this with us. I know you were heavily involved in the development of Vcm12 as well. It's good to kind of see what that has led to here. Oh, we got another question. Can RF inductively coupled plasma be simulated?
I have not done that. I know inductive is more complicated than capacitive in terms of the plasma production sense. I would be happy to talk more about that offline, or we could get in a conference call with one of the AEs on that. But it would, I think, depend on the kind of problem you're trying to do, and yeah, that's the short answer. We need to look at what you're trying to do and the degree to which we have all the tools in place for you to do it. I think there would be a time scale issue that would be relevant. And
sure.
So,
sure. And you can send sales@txcorp.com is kind of our general email. So if there's something specific that you've seen today and you really want to get more information on that, you can certainly send us an email that way, and we can get some answers for you on that. So any final questions before we break for the day? Tonight we are doing a encore presentation of the one that we did this morning with Dr. Andy Yu. So if you were not able to see that one and you want to see it live, once we have finished the event, we are going to have videos of all of our presentations. They will be on the TechX YouTube page. We will also have the presentations eventually will be uploaded to the TechX website as well. So we can try to get this information out to you. It looks like, okay, I think that is it right now. Okay. Great. All right, guys, I think that is it. I look forward to seeing you all tonight, possibly, or certainly by tomorrow. Thanks so much. Thank you, Tom.
thank you.